All right, so today we'll talk about semi-supervised learning. And we started talking about this last time in the context of semi-supervised SVM, but today we'll talk about it more generally. And in terms of readings, there is a very nice survey by Jerry Zhu that has that appeared in Encyclopedia of Machine Learning, and I'll post that on the website. Okay, cool. But just to put this into context, so for most of the classes, you guys know, we've been talking about learning from fully labeled data, right? This is for most of the class, except, and in particular for most of the class, we've been talking about the distributional learning setting. So except for a couple of lectures, one lecture by Tom and one lecture by me. Tom had the lecture about semi-supervised kind of naive Bayes, and also had a lecture about online learning. Except for those two lectures, for most of the class, we really refer to this distributional supervised learning setting, where we assume that there is some source of data. For example, there is an underlying source or underlying distribution over the space of email messages if you want to do spam detection. And then we assume that in the training phase, first a random sample of this data. So we first get a random sample from the data distribution, and we assume that this random sample is first labeled by an expert. And then so the learning algorithm gets a fully labeled sample. So it gets an ID sample drawn at random from the underlying distribution that is labeled according to something but a known target function. Okay, and what the learning algorithm that does, it outputs a hypothesis function, which could be like a decision tree or a linear classifier and so on. And our goal was to make sure that the hypothesis function that we output has small error rate on new samples that come from the same underlying source. Right, so this is basically the model we've been talking about, and this is in this framework we've been analyzing algorithms like naive Bayes, logistic regression, SVM, AdaBoost, and so on. Right, so we provided both algorithmic results, efficient algorithmic results, and also we talked about fundamental sample complexity issues, addressing questions of the type: how much data do we need to see in order to be confident that if we apply these algorithms like naive Bayes, logistic regression, SVM, AdaBoost on the sample, then we are guaranteed to output a classifier that has small error rate with respect to new samples that come from the same underlying source. Okay, so this is a typical, the usual, the classic supervised learning paradigm. This has been long studied in machine learning, and this is what we mostly been talking about so far. Okay. However, as I mentioned last time, so this has been great. This fully supervised learning scenario has been great. A lot of progress has been made and lots of applications. However, as I mentioned last time, this paradigm is basically insufficient for the modern age of big data, right? And we discussed that most modern machine learning applications have massive amounts of raw or unlabeled or undated data, right? So for instance, I mean, for most machine learning applications, we have so much data that is impossible or hopeless for humans to sit down and annotate or label it all according to our desired learning task. Okay, so for example, there are, I mean, if you want to do computer vision, there are huge collections of images on the web. You know, there are all sorts of many video sequencing, like lots of video data, for example, from surveillance cameras, wearable cameras, and so on. So huge amounts of data. Similarly, if you want to do some sort of information extraction, there are billions of pages on the web. Also, in computational biology, I mean, data is acquired at a really spectacular speed, right? We have so much data, and it's hopeless to have humans annotate it all. Okay. And so that's why there has been a lot of effort and interest in machine learning in the past 15 years or so in designing learning techniques that most effectively utilize the available data but minimize the need for expert or human intervention. Okay, and there's been a major theme in machine learning, and today and next time we'll be talking about two paradigms that attempt to do this, to somehow use unlabeled data while minimizing the need for expert intervention. Namely, today we'll talk about semi-supervised learning, and next time we'll talk about interactive learning. And these are actually learning paradigms where there's been great progress both at an algorithmic level and at the foundational level. And exactly address these four issues. Somehow trying to most effectively use the available data or the available data, but minimize the need for human or expert intervention. Okay? And we've been through this last time, but just to be again concrete and specific. So in the semi-supervised learning scenario, so in addition to a set of labeled examples drawn at random from the underlying distribution, so in addition to the typical channel where first a random sample of examples is labeled by an expert, according to our target function. So in addition to this set of, in addition to having a small ID set of labeled examples drawn at random from the underlying distribution, we also assume that the algorithm gets to see a large set of unlabeled examples drawn at random from the same underlying distribution, right? So in addition to this typical channel, we also assume that the algorithm gets to see a large ID sample from the underlying distribution. Okay, and then the goal of the algorithm is again to output a classifier that has small error rate with respect to the given unknown target function and with respect to the given unknown underlying distribution. Okay, so that's formally the model. So basically, in addition to random labeled samples, the algorithm also gets to see a large ID sample from the underlying data source, and the goal remains the same as before, to output a classifier of small error. Okay, so semi-supervised learning is pictorially. Okay, and as we discussed, this has been a major topic of research in machine learning in the past 15 years. With lots of activity, many methods have been proposed, many celebrated papers, lots of workshops, there have been even books written and surveys about the topic. So lots of great activity has happened on this topic in the past 15 years. Right, it's one of those topics that has both widespread applications and nice foundational understanding. So that's cool. Okay, in terms of the class today, what I want to do, so last time we already discussed the transductive SVM algorithm, which is a specific type of semi-supervised learning algorithm. And in terms of the class today, what I want to do, I want to go through these three major types of semi-supervised learning techniques. So I already mentioned last time, so one of them would be transductive SVM, another one would be the code training method due to Avrim and Tom, and a different set of techniques, kind of the graph-based methods, graph-based semi-supervised learning methods. Okay, they're all very, very different types of techniques, but somehow exploit the unlabeled data in very different, but also very interesting and creative ways. And so I think they're all very interesting, so that's why I'm going to go through each of them a little bit. And then I guess at the end of the lecture, when we'll step back and try to think a little bit more high level, in what sense is unlabeled data helping us? Because this will be all very, very different techniques, and we can think a little bit more, is there a fundamental underlying principle that makes unlabeled data informative? But we can talk about it at the end of the lecture. Okay. Right, and I think these are three of the major type of techniques that have been used for incorporating unlabeled and semi-supervised learning. There are other ways in which unlabeled data can be informative, but for my lecture today, I'm mostly focusing on very aggressive methods. So there are other ways, like Tom would know, like the Schurman's work or some even other ways, but those are non-aggressive. So I'm really focusing on methods that can very aggressively use unlabeled data. All right, so let's go slowly through each of them. Cool. So the first one is, and this is something that we already discussed last time, and we discussed it last time because it was very natural given that we talked about SVM right before it. The very first one is the transductive SVM method due to, oh, actually, right. I'm going to skip, actually, before even talking about this method, let me just mention just a little bit of, I mentioned it last time, but I mentioned it again, right? So in the semi-supervised learning scenario, at first, it's a bit puzzling or unclear what unlabeled data can do for us, right? Because somehow it is missing the most important information, right? What we really want to do is to predict the label, right? But unlabeled data is actually missing the most important information, the label, right? So then it's really unclear in what sense and when and why unlabeled data can help us, especially in substantial ways. Okay, you can maybe see more minor uses, but if you want unlabeled to help in substantial ways, it's a bit unclear what it can do for us. Okay, and it turns out that at a very high level speaking, and we'll come back to this later after we go through each of the techniques. So at a very high level speaking, actually unlabeled data can help us if somehow we have, our beliefs about the problem or our inductive bias is not only about the form of the target function, for example, what is a linear separator or decision tree, and so on. So right, enable data is helpful if our inductive bias is not only about the form of the target function, but also about how the target function relates to the underlying distribution. Okay, this is what will make unlabeled data very informative and very useful in very aggressive ways. Okay, cool. So, and let me go through each of those major algorithmic techniques one by one. And I'm going to start with semi-supervised SVM. We already discussed it last time. I'm going to recap it briefly because it's useful for the bigger picture. Okay, so this is an algorithm due to Thorsten Joachim's, and the underlying belief here is a very natural one, namely that it's a margin-based underlying belief, right? So here we assume that not only the target function separates positive examples from negative examples, but that it does so by a very large margin, by a reasonably large margin. Okay. And here is a picture. I think everyone, actually, even when I talk about semi-supervised learning to a more general audience, I think this is a picture that somehow always helps people understand what unlabeled data can do for us, even for people who do not know machine learning necessarily. Okay, so here is a picture. So let's assume, just for simplicity, that the target function is actually a linear separator. I mean, we can always kernelize it, but let's assume it's a linear separator. And let's assume that, and the belief now that underlies the semi-supervised SVM type of algorithm is that this linear separator does not cut the high density regions of the space. So in other words, the target function not only separates positive examples from negative examples, but it does so by a large margin. Okay? And under this assumption, then unlabeled data becomes very informative, as this picture shows. Why? Because conceptually speaking, it can help us to throw out unreasonable hypotheses. So those hypotheses that do not have a large margin. Okay? And so, for example, right, so here is this picture. So like if we only have 4 labeled samples, right, a very, very tiny amount of labeled data, then what SVM will do would output the maximum margin hyperplane over this set of labeled examples, right? So it output this purple, dotted purple hypothesis, okay? Now, however, if we start seeing unlabeled examples, then we quickly realize that this separator actually does cut through high density regions of the space, and so it's not so reasonable after all. And so we're going to throw it out, okay? And then once we see lots of unlabeled data, like this is what the classifier that the transductive SVM would output, is one that has a large margin over both labeled and unlabeled samples and gets the labeled data right. And in this picture, in this specific case, this happens to be the target function. Okay, so is this picture clear to everyone? So basically, if the large margin belief is truly correct, then unlabeled data can be incredibly useful because it can help us throw out hypotheses that do not have a large margin. And so then we could learn with much fewer labels. Any questions about this? Okay, so that's the picture, right? That shows that somehow if truly the data does have a large margin, then unlabeled data can be incredibly helpful because it can help us throw out hypotheses that do not have a very large margin, even if they get the labeled data right. And somehow reducing the search space conceptually from the whole set of linear classifiers down to only those that have a large margin, and so then we would need fewer labeled examples to pick among those. Okay, and that's basically the basic idea here. And then, given this basic idea, and we've been through this last time, then Thorsten Joachims in his 99 paper, what he did, he just basically wrote an optimization, like a constraint optimization problem that finds a separator of large margin over both labeled and unlabeled points, subject to getting the labeled points right. Okay, and right, and this is, I'm not going to go through the details, but so like basically in addition to constraints about labeled data, now we'll also have constraints about unlabeled points. We want to make sure that the unlabeled points have a large margin. As we discussed, actually, right, and this is for the realizable case where we truly, where the data is truly linearly separable. You can also relax to the case to handle some outliers, right, where the data nearly has a large margin, and we can use the same trick that we did for supervised learning, or we add select variables, right, to allow the points to violate, to actually be on the wrong side if the data is noisy and potentially not even linearly separable, right? So we allow the points to be on the wrong side, but then we pay, right, in the objective function, we pay through a slack variable the amount of, but we have to move the point to put it on the right side by the right margin. Okay, so we do the same both for labeled and unlabeled points. Okay, and then we pay this, right, so, and then we get this constraint optimization problem that corresponds to the non-separable case. Now, as we discussed actually last time, and let me actually just mention this again, right? So if we only had label data, right? So basically, if we only had label data, and our SVM program would look like this, right? We only have, this will correspond to try to maximize the margin and also minimize the total distance we have to move the points to get them on the right side by the right margin, right? So it only have, this would be the objective, and this would be the label, the constraints given by label data. And as we discussed, in that case, actually, the problem becomes a convex optimization problem, right? Because we have a convex objective, like a quadratic objective, subject to linear constraints. So if we had only label data, this would be solvable in polynomial time. However, by using standard techniques. However, once we introduce the unlabeled data constraints, intuitively speaking, because once you have the unlabeled data, suddenly you have choices on which side of the separators each point should belong to. You have kind of many choices, then you can formally show that the problem becomes NP-hard. So even with the slack variable, even with this relaxation, the problem still remains hard. So this optimization problem in this form is NP-hard. Okay, so I guess unlabeled data can be very helpful. It can help us save label complexity, but typically the corresponding algorithmic problems are much harder from a computational point of view. So it's interesting because you have to think about that. We cannot just apply, classic tools. But it's interesting. Cool. And right, so the natural transductive SVM or semi-supervised SVM adaptation of supervector machines leads to an optimization problem that is NP-hard. So it's believed to be very hard, right, under classic complexity assumptions. However, Thorsten, right, and the basic problem is that the problem is convex only after we guess the labels of unlabeled points, but there are too many guesses for the labels of unlabeled points, essentially. Okay, so it's NP-hard in its basic form, but then Thorsten, nonetheless, really wanted to try this idea on real-world data, and then so he came up with very natural local search heuristics that he tried on data. So, for example, the technique that he tried to do at a very high level speaking, we can read more details in his paper. Right? So the technique that he tried is the following, where he first maximize the margin over label points, and then use the corresponding classifier to assign labels to unlabeled points, and then try to flip the labels of unlabeled points to see if we increase the margin, and then repeat all this. It's kind of a local search procedure that he tried. This finds a local optimal solution, and then he showed on real-world data that actually this leads to improvement over basic SVM or over naive Bayes on some data sets, on some, I guess it was information extraction type of problem. Okay, so even if the underlying problem is NP-hard, we can think about some natural heuristics, kind of local search heuristics, and then he did do so, and then experimentally prove the benefits of this method. Okay, so that's transductive SVM, which essentially is based, or semi-supervised SVM, which is really based on the underlying assumption that makes unlabeled data informative in this case is that the data, the target function not only separates positive examples from negative examples, but it does so by a large margin. Okay, cool. And we already went through, mentioned this last time, but I think it's nice to think about it again. So you might wonder, well, if my assumption is truly satisfied, if truly I have a large margin assumption, is unlabeled data always helpful? Okay. So, and the answer is interesting. It turns out that it's not always helpful, even if I have a large margin. So because we can construct, so even if I have a large margin, if truly the target function is a large margin, unlabeled data might not always help. Why? Because we can essentially construct, the pictorial is this picture over here, we can always come up with 1 over gamma squared. So say that you know the margin, I tell you the margin is gamma, right? It's a number between 0 and 1, right? Even if I know the margin gamma, I can always come up with 1 over gamma squared blobs that are all separated by margin gamma. So in other words, here there are 2 to the 1 over gamma squared possible labelings of these blobs with large margin separators. And the target function could be any of those. I could pick the target function for random among those. And if I do so, unless I see a label point in each of the blobs, I'm not going to be able to know what is the label inside the blob. Right? And so, okay, and why is this not good? Because I'm claiming that this example shows that even if the large margin is satisfied, even if I know the margin gamma, then I still need 1 over gamma squared label points. And why isn't, okay, so, and what's the problem here? So I claim even if I have like huge amounts of unlabeled data, infinite amounts of unlabeled data here in this example, I'll still need 1 over gamma squared label points because I'll still need to see at least one example in each of these blobs. Now, why isn't this good? Because, well, it's not good because, as we discussed, if we have a large margin, we already mentioned this, how many supervised learning, how many labeled examples? How many labeled examples do we actually need for supervised learning? So if the underlying problem, right, if I have a classification problem, the target function is the large margin gamma, how many labeled samples do we need for supervised learning? Just purely supervised, no unlabeled data. I think we're introducing these class participation points. And people that do not show up to class, we're going to take points off. Okay, now I don't need to read it. Right, so if we had only, if we had labeled data, so if we were in the purely supervised learning scenario, right, all the examples are labeled, and if we did have a large margin gamma, right, how many examples would we need to generalize well? We discussed this a couple of lectures ago, yeah? You want to try? Say it, yeah? Exactly, R over gamma squared, right? Good. So here, absolutely. Here I also assume, okay, that's actually a perfect point. Here I'm assuming I'm simplifying things. Here I'm assuming that all examples have unique length at most unique length at most one, right? So you are Hirsch, right? As Hirsch is saying, if we had a margin gamma, especially if we normalize all the samples to have unit length, or at the most unique length, to have length at most one, then the number of labeled examples needed for purely supervised learning is 1 over gamma squared, right? Because I normalize the radiosity at most one. And this is a sample complexity of SVM or perceptron in the scenario, right? So if we had this world where we have truly have margin gamma, right? For any of these possible, right? For any of these so here we have 1 over gamma squared blobs. There are 2 to the 1 over gamma squared possible labelings of these blobs with large margin separators, right? And the target function could be any of them at random, right? In that case, we would need only 1 over gamma squared label points to learn well by a supervised learning scenario. But as I argued in this case also, even if we have access to unlabeled data, we still need 1 over gamma squared label points because we still need to see at least one example here, at least one example here, at least one example here. Right? So this is an example where unlabeled data doesn't help even if you have a large margin assumption. Okay. Now, can somebody argue why actually? So this is one case where we have many blobs. However, if we have much fewer blobs, right? If we have only say a constant number of blobs, if the distribution, the underlying distribution is nice, but only I have a large margin, but kind of like in this picture over here, I only have kind of say 4 inherent blobs in the underlying data distribution. When I claim that unlabeled data can help us a lot here. Do you guys see why? So informally speaking, yeah? So informally speaking, like for example, this is an example where the data is the underlying distribution is very nice with respect to our belief. Because we have only, say, 4 blobs separated by a large margin, right? And we know that the target function doesn't satisfy the region of the space, right? So kind of how many possible, very different choices still remain for the functions, for the target function once we see unlabeled data, if we have 4 blobs. Yeah, you are saying. If I have 4 blobs and I know that the target function cannot cut through any of these blobs, right? Because if it cuts, if a function cuts through any of these blobs, doesn't have a large margin, right? and if I have 4 blobs, and I know the target function doesn't cut through any of those 4 blobs, only 2? There are potentially more, right? Because it could also, this also would have a large margin. Okay, do you see here, I'm thinking about them as being 4 blobs really. But, right, if I have, so let's assume that I have 4 blobs. So let's assume that these are a little bit more separated, right? So I want to make this a bit more interesting. So let's assume that really the margin here is large. So I really have 4 blobs. Like how many possible choices are for the 6? Why 6? Okay, I think there are more. I think there are a few more, right? I can label each of the blobs as positive and negative, right? There is a target, there is a large margin separator to label each of these 4 blobs as positive as negative, right? In this specific case, if we're really separated by a large margin. So then we need, I think, there are 2 to the 4 possible labelings left, right? And so all we need in conceptually enough label data to distinguish among those 2 to the 4 possible labelings. Okay? In any case, the point is that if the data is nice and it truly has, rather than having many, many underlying blobs that are separated by a large margin, there are only much fewer blobs separated by a large margin, then unlabeled data can help drastically, because after we see unlabeled points, there are only much fewer types of functions that separate, that kind of, that do have a large margin with respect to the underlying distribution. So in this specific case, if we had truly 4 blobs separated by, like, if my data was like this, 4 blobs, right? All separated by margin gamma, then I only have 2 to the 4 possible functions that we're gonna separate these blobs by large margin, and my target function would be one of those. So I just need enough examples, labeled examples, to choose among these 2 to the 4 possible functions. Okay, so this is intuitively speaking what unlabeled can do for us in this semi-supervised large margin setting. Okay, and of course also if the margin condition is not satisfied, like if this is the distribution is uniform in the unit cube, then obviously unlabeled will not going to help us at all, right? Then we need lots of labeled examples, both in supervised, fully supervised, and semi-supervised learning scenario. I mean, here you can just generate the data yourself. It doesn't help if the assumption is not really satisfied. Okay, so basically even once we have this belief about how the target function relates to the underlying distribution, we still have more helpful and less helpful distributions with respect to this belief. Okay, and this is illustrated via this example. But anyway, the point is that if we're lucky and the data is nice, like this one here with respect to the underlying distribution, then we need much fewer labeled examples compared to purely supervised learning. Okay, so this is one type of, so large margin is the one type of assumption that makes unlabeled time formative. Okay, but it turns out that there are many other types of assumptions that will make unlabeled time formative. Okay, and I'm going to go through the 2 more examples, and you'll see that they're kind of fun because they're all very, very, very different. Okay, and the next one is I have to talk about the co-training assumption, or the agreement between 2 parts. So there is a very interesting semi-supervised technique called the co-training technique, which is based on a very different assumption compared to the large margin assumption. And namely here the assumption is that some sort of consistency between 2 parts of the example. Okay, and all right, so I have to teach this, it's only in the room. So it's very interesting. Cool. So yeah, so this is due to Avrim Bloom and Tom Mitchell. Avrim was my PhD advisor, I mentioned this last time. Okay, so here is actually, we can describe this by a picture actually. So it's best to introduce this semi-supervised learning technique by an example. Okay, so imagine that, right, so this semi-supervised learning technique is useful in situations where for our learning problem, we have 2 natural, very different set of features, okay, that are somehow redundantly sufficient, they're kind of redundant, and each of them in principle is sufficient for correct classification. Okay, so let me go more slowly through this. Actually, this is an example from the original paper. So let's assume that we are trying to classify web pages as being faculty members' home pages versus non-faculty members' home pages. Then, in this case, we could, if we think about it, we could try to classify our web page by using the words inside the web page itself, right? So this would correspond to a first set of features. right? So we could just come up with features that only are based on the words that appear inside the web page. Okay, this is the first set of features. But if we wanted, we could also classify we could classify the web pages by using the words from the hyperlinks pointing to the web page from other web pages. Okay, so these are two different types of features that we could use for classification. And by the way, when I was a student, this is how these words would be in the hyperlinks pointing from my web page to my PhD advisor web page. Okay. So right, basically for this web page classification problem, right, we have two very natural, very different set of features. So we could use for classification the words inside the web page itself. So therefore, this would be the first set of features x1 for an example x. Or we could use for classification the words from the hyperlinks pointing to this web page from other web pages. And if you think about it for this example, it's natural. I mean, it's in principle you can correctly classify a web page by only using either the first type of information, the word inside the web page itself, or you could actually even correctly classify it in principle. You can achieve high accuracy by only using the words from the hyperlinks pointing to the web page. Okay, so now the underlying, basically the belief that underlies the co-training technique is that in principle each of these parts kind of sufficient for correct classification or sufficient for achieving high accuracy, and moreover also that the two parts of the examples are consistent. So in other words, given an example x, which is now a pair, right? For each example x, I have now two sets of features. The first set of features are denoted by x1. The second set of features are denoted by x2. And so given an example x, the belief that underlies the co-training example is that these two parts of the examples are consistent. So for example, in the extreme case, or we truly believe the belief, or we truly believe that this set of features are sufficient for correct classification, then we would think about like in that extreme case, it will be the case that there exists two target functions, one for the first view, and another C1 for the first view, and another one C2 for the second view. So that basically, given an example X, C1 perfectly predicts a label on that example by only using the first set of features, and C2 perfectly predicts a label on that example by only using the second set of features. Okay, so that's the setup. Now, why is this interesting? Okay, because I just told you what the setup is and what is the underlying belief of co-training. Right? So co-training works in cases where we have problems, where we have two natural and very different set of features that are in principle sufficient for correct classifications that are consistent. Okay, this is what I said so far, but why is unlabeled are helpful in this scenario? Okay, and this is an idea, I guess, due to Tom. Okay, so why is it helpful? Well, because if you think about it, we can first, this is the idea behind the iterative co-training algorithm, okay? So why is it helpful? Because if you think about it, we can first use a small set of labeled examples to learn some initial rules that when predict, they are correct, but perhaps they don't predict too often. So we can learn some weakly useful predictors by using an initial set of labeled examples. So for example, from a small set of labeled examples, by using the second set of features, so the words from the hyperlinks pointing to the web page, we might learn, right, that when a web page has the words my advisor pointing to the web page, then this is a good indicator that web page is the faculty member's homepage, right? So remember here my goal is to classify web pages as being faculty members' homepages versus non-faculty members' homepages. Right? So it could be that from a small set of labeled examples, I could learn that, for example, right for the second view, the second set of features, if a web page has the word my advisor in hyperlinks pointing to it, then this is a good indicator that is a faculty member's homepage. Okay, or for example, I could also learn, again from a small set of labeled examples, that now I'm thinking about the first set of features, right? Which is, so what is the first set of features based on?
Text.
Yeah?
Text information.
Text information inside the web page itself, right? Good. So the first set of features was based on text information inside the web page itself, and we can learn potentially from a small set of labeled examples that if the web page has the phrase I'm currently teaching a certain course, then this is a good indicator that this is a faculty member's homepage, right? This is very sensible, right? So you could learn some rules from a small set of labeled examples, rules that are, when predict, they are confident, but they might not predict always. Okay. Now, so why is it interesting? Because now we can use the unlabeled data to propagate the learned information. Okay. And right, so basically, right, from a small set of labeled examples, maybe we'll learn some weak prediction rules on each of the two views, on each of the two sides, right? And then we can look for unlabeled data, and if we see an unlabeled point or one of the two rules is confident about the label and the other one is not, we can ask the confident one to label the example for us, and we can fit it as a label example on the other side. Okay, and we can use that newly acquired label samples to retrain our rules on each of the two sides. Okay, so basically, right, so for example here, right, so it could be, right, based, that now, right, we now go for unlabeled data, right, so we have first weak rules H1 and H2, then we go for unlabeled data, and then suddenly we notice that one of the classifiers is confident about, so for example, this classifier, the second class, maybe the classifier based on the first view is confident about this example, but the other one is not. We can ask the confident one to label it for us, and we fit it as a label example on the other side. And then we retrain our classifiers on both sides, and then we iterate. Okay, so basically in this code training view where we have two redundant set of features, unlabeled data can help us somehow propagate learned information. That's the basic idea. Okay, and here is basically more schematically the algorithm, right? So what we do here is initially we're gonna, at each moment in time, we're gonna have two classifiers, one for each of the two views, right? Two current classifiers, one for each of the two views, H1 for the first view, H2 for the second view. Initially, we learn this classifier from a small set of labeled points. We learn a classifier H1 on the first view and classifier H2 on the second view. And then we iterate through the following process. Right, so when we repeat, right, we look through the following. We look through the unlabeled data. And if we find one example or one of the classifiers is confident about the label of that example, but the other one is not, we ask the confident one to label it for us, and we fit it as a label example on the other side. Okay? And then we retrain the two classifiers, H1 and H2, and everything repeats. So is the idea clear here? Okay, cool. And right, and basically, maybe I'll come back to this later. So this is the main idea, right? In the original paper, the code training idea, right? And I guess in their paper, Avim and Tom showed actually that this idea is very valuable for this web page classification problem. So they showed actually that if we do code training, we do better than just doing, so if we do code training by using, right, so we need to specify these learning algorithms, right? On each of the two views, you need to have a learning algorithm, right? Given a small set of labeled examples, what is the underlying learning algorithm, right? And I guess in their paper, Tom and Avrim used the naive Bayes algorithm on each of the two views, right? And they compare it against the naive Bayes overall, and they show that this does much better when you have very few labeled examples. So, for example, if you have only 12 labeled examples but lots of unlabeled data, if you do code training, you'll do much better than just doing purely supervised learning with 12 labeled examples only. Okay, so this is the example in the original paper. But actually, I want to spend one more minute, because the idea is very natural, but I want to also go through a little bit of a more formal example illustrating what code training does. To make even more apparent how in the code training scenario actually we can use unlabeled data to propagate learned information. Because you see, this, I think this is really interesting. It's very, very different from the margin assumption, right? It has nothing in common when you think about it. It's a very creative use of unlabeled data here, right? Okay, cool. So I'll go through this example more slowly. So let's assume, just for simplicity, this is a toy example, by the way, but it illustrates some good points, okay? So let's assume for simplicity that basically, right, so as I said, in code training, we need to have two sets of features. So each example has two sets of features. So we have a view x1 and a view x2. We also call them views, two different views, right? And let's assume that, I'm assuming here for simplicity that on the view x1, the target function is an interval, right? So this will be an interval. So I'll predict positive, right? So this will be my target function. This will be the first set of features. So this, oops, what did I do? I have to go back just a second. I guess by mistake I skipped to the beginning. Okay, so here I am. Great. So let's assume, right, so this is the first set of features, basically. So this is x1, this is x2, right? So the instance space for the first set of features. So basically the first feature is just a number, right? And let's assume that the target function over the first view is basically is an interval, right? So here I would predict positive inside and I would predict negative here, right? Okay. And similarly, the target function for the second view is again an interval. I would predict positive here and negative here, right? And so let's assume that this is a word. This is how the word looks like. Now, to have agreement between the two parts, if you think about it, also it will mean that I cannot, for example, I cannot have any probability mass here, right? So to really have agreement between the two parts, which will mean that, for example, I cannot have any probability mass here. Pink color. Okay, let me try this green. Right, I cannot have any probability mass here, right? Because here, for example, this would be an example where the first target functions predict negative, but the second one will predict positive, right? So pictorially, right, if you think about it, what this agreement between the two parts means a certain part of the instance space has zero probability mass. Okay, good. But so let's assume that that's the case, and let's assume that basically our distribution looks like this, right? So this is a kind of the distribution in the two views, right? This is the first view, this is the second view. In the first view, the target function is an interval. In the second view, the target function is an interval as well. And let's assume that I only have probability mass in these blobs over here. So I have probability mass here, here, and here in the shaded blobs, yes? And obviously, this will be the positive region, and this will be the two negative regions, okay? Now, let's think about it. How we can do code training. Okay, but before even talking about code training, let me just mention that if we are in the supervised learning scenario, right, and if I'm trying to learn an interval, if I have a purely supervised learning problem and the target function is an interval, it turns out that we can easily learn an interval function by just always finding a classifier that, so let me mention this because that's important. Before going on, maybe I'll go here. Maybe I'll just go here, right? So for example, if I'm trying to learn intervals on the real line, because that would be important here, right? So let's assume that the target function looks like this. This is my target function, right? Now, if I get a few points at random, so I'm going to get a few positive points and a few negative points, okay? One natural algorithm to learn the interval is to just find the smallest interval that encloses the positive examples. If I find the smallest interval that encloses the positive examples, that has a nice feature. If this is my learning algorithm, it has a nice feature that whenever that algorithm says positive, it's always correct. Okay, and you can always show that, and you can also show that if the number of samples you see is of the order 1 over epsilon, then you also good generalization guarantees. Okay, so this class of intervals has a nice property that you can learn it, you make no error, so if you can come up with a hypothesis that makes no error when it says positive. So when my hypothesis is going to say positive, I'm confident it's correct. Okay? So again, here the learning algorithm, if I'm trying to learn intervals, this is my target function, so an interval. The learning algorithm would be I just draw a bunch of labeled examples, and then I'm just going to output the smallest interval that contains the positive examples. That's a nice learning algorithm because not only has good sample complexity, you can show that you need few labeled samples to learn well, but also with the hypothesis that I output has the property that whenever it predicts positive, it will be 100% correct. Okay, so let's use this for our code training example, because what I really want to do is talk about code training. Okay, because this will show, I think this picture will illustrate what code training can help us to do in a more formal way. Okay, so let's assume that we have two views. This is the first view, and this is the second view. And, right, so the target function over the first view, let's assume is this one over here, C1, and the target function over the second view is this one over here, right? Now, let's assume that we see a small set of labeled examples, like these dotted red examples, right? Now, I'm going to just apply iterative code training. So if I see a small set of labeled examples, what is the first hypothesis that I learn on the first view by using the algorithm that I mentioned for learning intervals? Yes?
Can you show the lengths that are on this projector so we can't see the lengths?
What should I do? I should...
Just the projector lengths.
Okay, Travis will help me.
Just medium lengths.
Oh, that's much better. Okay, great. Good idea. Cool. Right, so let's apply the co-training algorithm here, and let's assume that we see a first set of labeled examples, right? So let's assume that these red examples are our so the red examples are the labeled for us, and the rest are unlabeled. You see, guys, there are these also unlabeled examples over here, right? So what would be the hypothesis that we learned by using the labeled samples? I claim that in the first view, we're going to learn this hypothesis. Why? Because when I project the labeled examples of this first view, this will be the smallest interval that contains all the positive examples. Okay, and similarly for the second view, this will be the first hypothesis that I learned based on labeled data only. Why? Because when I project on this second view, this will be the smallest interval that contains all the labeled examples. Okay, so this is the first part where you just use labeled data to learn two initial hypotheses, right? And these two hypotheses have the property in this the way I start the example that when they predict, when they say positive on an example, they are always correct. Okay, now we can use unlabeled data to co-train them. Okay, and in particular, let's think about this second classifier, right? So this classifier over here, so what we learned on the second view is that when an example falls in this interval, it's always positive. We know that, right? We learned this from a small amount of labeled data. But now we can go and look, there are some examples, unlabeled examples, like these very light dots over here. These are unlabeled. There are some unlabeled examples that this classifier currently will be able to label. Okay, and the other classifier on the first view is not able to label them, right? So these are, for example, right, these examples over here, these guys, and these guys, right? So these are examples where the first classifier will be confident about their label, but they are positive, and the first guy is not confident, he's not able to label them at all, right? So we're going to ask this guy to label them, so then now they will become positive examples for this first view. Right, so now they'll become positive examples, and now we can then retrain our classifier on the first view, and so now we can expand the classifier for the first view. Right, so after this round, then this will be the classifier for the first view. Right, and then again, I can go again and do the same trick. Right now, this classifier is confident about, for example, this classifier now in the first view is able to now label these unlabeled points. Right, and the classifier that we currently have for the second view is not able to predict on those. Right, and we can ask the classifier for this classifier to label this as now will become positive examples, and then we can feed them as a labeled example for this other view, and now we can update our classifier for the second view too, and so on. Basically, we use unlabeled data to propagate learned information. So in this example, there are moments where one of the classifiers, like this one here, is confident about the label of some examples. The other one has no idea how to predict them. We ask the confident one to label it for us, to label those examples for us, and then we feed them as the labeled examples to the other classifier. Okay, and then as you can see in this pictorial example, after a few rounds, we almost got the target functions on each of the pictures. This is really interesting. We basically use unlabeled data to propagate learned information. So is this picture clear? Yeah, I think it's a picture that illustrates the power of co-training. It actually is a great picture because actually it can help also make me make another point actually. In co-training as well, as you mentioned for graph-based, for the large margin type of semi-supervised learning I already mentioned, it's not always the case that unlabeled data is helpful, even if the assumption is fully satisfied. Right? Now, for the co-training case, even if the assumption that the two parts of the examples are sufficient for correct classification and consistent, they agree with each other, that even if that assumption is satisfied, the underlying assumption is satisfied, is not always the case that unlabeled data is helpful. I still need a helpful distribution. Why? Because, for example, if I go back to my intervals example, well, so this was a nice distribution that allowed me to somehow kind of propagate information. So I first can learn some weak learners from unlabeled data, and then I can use from labeled data, right? I can first learn these weak learners, H11 and H21, and then I can use unlabeled data to propagate learned information. Okay, but this was the case because somehow my distribution has some nice expansion properties. If instead my distribution was a nasty distribution, but if I only had mass on the examples of x1 equals always x2, so like in this picture over here, right? And then let's assume that the agreement between the two parts is still satisfied. So if, for example, here I set up the problem so that I can still correctly classify an example by using only the second view or by only using the first view, and I still make sure that I have but consistency is satisfied. So basically, I have no probability distributions when the parts of the instance space of these two classifiers disagree. So I only have probability distributions where they agree. So the agreement between the two parties is satisfied. Even then, I can still have a distribution where code training is not helpful at all. Because what happens if I only have probability mass one examples where x1 equals x2? Then there is nothing that we can propagate, right? Do you guys see why? So basically, if my distribution is just over here, right? x1, I only have examples x, which look like a pair, x1, x2. So, but always x1 equals x2. Do you guys see why unlabeled is not helpful? There is nothing to propagate, right? So that's interesting because this picture shows that actually for unlabeled to be helpful, we need to somehow have some niceness property in the underlying distribution, some sort of expansion property. Okay, and indeed people have proven some formal guarantees about code training, right? So this was, as I mentioned, basically in practice the algorithm is great, but also you can also analyze it formally. Okay, and these types of pictures are crucial for trying to understand formally when unlabeled can help us for code training. So yeah, is this clear why, for example, here, if this is a distribution, there is nothing, no way to propagate learned information, right? Because especially if I use the same learning algorithm here, right, this class on a small set of labeled examples is to be the part where the first classifier is confident, but this is identically the part when the second classifier is confident. So there will be no example where one of them is confident about the label and the other one is not. So there is no way for me to use unlabeled data to somehow co-train that. Okay, cool. Right, so that's the picture, but now in terms of formal guarantees, right, so let me mention a couple of them. So in order to think about, especially for iterative code training, in order to think about formal guarantees, you have to think about, to reason about two types of quantities. You have to think about what types of algorithms do I have on each of the two views, right? I kind of implicitly assumed when I describe code training, I implicitly assume that we have algorithms that have the property that when they predict, they are kind of confident, or at least I can put some confidence on their predictions, right? So we need to think about the types of algorithms that we have in each of the two views, and we also have to think about properties of the underlying distribution, right? Because as I mentioned, if the distribution is adversarial, like this one over here, has no expansion properties, then unlabeled data might not be helpful at all. Okay, and right. And in their original work, Tavrim and Tom showed is that actually a nice case where unlabeled data can be substantially helpful is one where you have independence given the label. So right, given that the label, so which means that basically given that the label of an example is known, for example, to be plus, then the two parts of the examples are independent given the label. This is one case that we are able to analyze formally. Right, so I guess you guys are all familiar with what independence given the label means, right? We've been using it throughout the course, right? And so in this context, for example, so this is a picture here, right? So, right, independence given the label means is like basically, let's assume that this is the first view and this is the second view, right? So this is the first instance space, the second instance space for the second view, right? And this will be like, for example, this will be the region. This will be the conditional given the positive region on the first view. This will be the conditional given the negative region on the second view. Sorry, this will be the conditional given the positive region on the first view. This will be the conditional given the negative region in the first view again. This will be the conditional given the positive region on the second view, and this will be the conditional given the negative region on the second view, right? And the independence given the label means that if once I decide that the label of the example is say positive, then I just pick the two parts of the examples independently. So I draw x1 at random from D1 plus, and I draw x2 at random from D2 plus, and I create an edge between the two examples, right? This is what independence given the label roughly means. And so if you think about it in this pictorial graph-like view, what independence given the label really means that these two components are very, very well connected. Okay, there are weights on them, but really roughly that's what it means. But the two components are well connected. Okay, so when in that world, you can then show that if Right, so if you start with a weakly useful predictor, right, or the original work showed is that if you start with a weakly useful predictor, which roughly a weakly useful predictor just means it's roughly something like a weak predictor if the two classes are balanced. Right, so if we start with a weakly useful predictor, and then we can use large amounts of unlabeled data to then achieve a classifier of arbitrary high accuracy. If we have the property that in each of the two views, our algorithms can learn from random examples. From random noise, are tolerant to random noise. Okay, this is roughly what the original work showed. Right, and we did need independence given the label. Actually, in subsequent work, we were able to show that actually independence given the label is not quite needed. All we need is kind of we just need to have some sort of expansion properties of the underlying distribution. So, and you'd still be able to prove a similar result. So, any questions? These are formal guarantees about code training. Explain pictorially, I guess. The key point actually to take away here is that really, in order to prove and actually right, in order to formally show benefits of unlabeled data in this scenario, you really need to have the distribution has to be somehow nice with respect to the underlying assumption. And the original niceness assumption was that basically the two parts of the example, so given the label, the two parts of the examples are independent given the label. Okay, and if so, in that world, then you can essentially learn from very limited label. In that world, right, basically, if you have enough label data to produce a weakly useful predictor, which is something like a weak predictor if the classes are balanced, then you can use unlabeled data to bootstrap the accuracy of that predictor to arbitrary high accuracy. Okay, I guess this was written here, right? So if we have enough labeled data to come up with a weakly useful predictor, which just means the details are not important. What really means a weakly useful predictor is like a weak predictor if the classes are balanced, right? And we know what weak predictors are. We use them for boosting, right? Right. So if we have enough label data to come up with a weakly useful predictor, then we can then use unlabeled data to bootstrap the accuracy to arbitrarily high accuracy by but if we have algorithms that can tolerate noise. Okay, and I'm going to skip the details. You are welcome to talk to me, Tom, or Abri if you are curious to find them out. Okay. All right, I just want to make one more comment, and then I want to actually, this is iterative code training, and I also want to mention a different type of code training algorithm, which is actually even more used in practice, I think. But just a comment before going on, I just want to mention that independence gives the label, and actually even, expansion, these are very strong assumptions in a certain sense, because they imply, if you think about it, what independence gives the label, and expansion implies that if you think about functions, so right, in code training we're always trying to look, this is a goal, right? I mean, implicitly this is our goal. We are trying to look for functions that agree, right? We are trying to look for pairs of functions, h1 and h2. If this h1 is a classifier for the first view, h2 is a classifier for the second view, and in code training what we are really trying to do by somehow use label data and also unlabeled data in a smart way, but at the end of the day, we are trying to look for classifiers that agree on examples, right? Right, we are trying to look for a pair of functions h1 and h2 with a property that they will agree. Often, maybe not always, but often they will agree. Actually, let me try this again. Okay, let me use a better color. Right, so in code training, essentially we are trying to look for a pair of functions, h1 for the first view, h2 for the second view. Like this will be a classifier that uses the words inside the web page, right? The first set of features, or this will be a classifier, h2 will be a classifier that uses the words from the hyperlinks pointing to the web page, right? And what we are trying to do in code training is somehow to use labeled data and unlabeled data in various ways. But at the end of the day, we're trying to find classifiers, pairs of classifiers that agree a lot on examples, on unlabeled examples. Okay, and now here's an interesting fact, actually, that kind of a little bit, this is high level, but I think is the right picture that, to think about what it means. So if we do have independence given the label or even expansion, it turns out that there are only kind of 4 different types of pairs of classifiers that agree on unlabeled data a lot. Okay, and those classifiers that are close to the target function. So H1 has to be close to C1, and H2 has to be close to C2. This is the first type of, right? So there are 4 different types of classifiers that agree a lot. The first one is close to the target function, close to the opposite of the target function, close to all negative, to all positive, or close to all negative. So independence given the label or even expansion implies that really there are, if I think about my underlying distribution, there are only really 4 different types of pairs of functions that agree. Okay, and this then immediately should imply that we need lots of labeled examples, few labeled examples in principle, because I only need enough labeled data to distinguish among these 4 different types of classifiers. Okay, and I'm not going to go, it's just again, just an intuition using this picture. Like, I'm not going to go for any of the details here, but in pictorially speaking, like if you had a classifier, for example, that was not one of these 4 types, maybe it was a classifier like this one here, right? That somehow it was like you have a pair 8, right? So if you have a classifier, okay, I'm not even going to do this actually, but assume that you have a classifier like this one here, that is perfectly, so the first one, H1 is correct, agrees with C1, but kind of H2 cuts through the positive region of the second part. Well, then we're going to see a lot of disagreement, because if this graph is fully connected over here, then I'm going to get, because it's fully connected and they have independence given the label, I'm going to catch this classifier as having kind of a high labeled error rate, because I'm going to catch a lot of disagreements, because I'm going to have good probability, a good chance of seeing an example here and an example here, and then they will disagree about the label. Okay, so we can use this type of picture to kind of explain why, if we have independence given the label, there are only 4 types of classifiers that have high agreement, which then implies why you could hope to learn from very limited label data. Okay, this is just in principle, because it's not clear that, right, this is just in principle. This reasoning wouldn't apply to any learning algorithm, for example. It wouldn't apply to the original argument that Tom and Darwin. Okay, cool, and I'm going to skip these details. I'm going to go to something more interesting from a practical point of view. So everything that I talked about so far is about iterative code training. However, it turns out that there is another way to do code training. So there is another way to do multiview learning, where we are just directly trying to optimize, write an optimization problem that exactly expresses our belief, right? So what is our belief here in code training? What are we looking for? Okay, maybe somebody can help me with this. Not Tom. I'm sure he'll be. Right, I mean, so far I presented this iterative code training viewpoint, which is like the one that kind of motivated the original work, but I claim that there is another way to just basically use unlabeled data. It's just directly like an optimization problem that expresses exactly what we are looking for, right? So I already mentioned in the previous slide, what are actually looking for when we do code training? We are looking for a pair of classifiers, one for each of the 2 views, right? I'm looking for, I switch here to F1, or could have been H1, but in any case. We are looking for a pair of classifiers, F1 and F2, one for each of the 2 views. And what do we want to impose? What is the underlying belief of code training? The underlying belief of code training is that those 2 classifiers agree a lot, right? Right? The underlying belief of code training is that the 2 parts of the examples are consistent and sufficient for correct classification. So in particular, the target functions on each of the 2 views are agree a lot on unlabeled points, right? So therefore, we can also just write down an optimization problem where we are saying we are looking for a pair of classifiers that agree a lot on unlabeled samples that come from our underlying distribution, and moreover, that have small labeled error rate, right? So you can just directly write an optimization problem. So we're going to be looking for a pair of classifiers, F1 and F2, right? One for each of the 2 views. And what we want to do is we want to impose agreement on the unlabeled points. And we also want to make sure that they have small labeled error rate. They minimize the loss over the labeled data. Okay, this is one short code training. And of course, there are many details, and many people have looked at many variations. What do you mean by agreement? What loss should we consider? Right? And if it turns out that if we consider a loss function, of course, we can consider, for example, the typical 0-1 loss. We can consider square loss. And for agreement, we can consider all sorts of notions of agreement, right? And there are many variations of these, right? But then they all capture the underlying belief of co-training, right? And if both the loss function and the agreement functions are convex, then we can also solve this in polynomial time, right? And there have been many, many works on this, doing this. Okay, cool. And I think this, so Tom would know better, but I think that this one-shot optimization problem somehow is loss tolerant to noise, because when I described iterative co-training, I was trying to tell you guys when it works and why it works. But I think that it's very sensitive to noise too, right? Because you can, if you have noisy points, you can potentially quickly start propagating kind of wrong information. But this one-shot optimization, I think it's less sensitive to noise. Right? Am I correct, Tom? Is it true in your experience? So Tom is the expert on the topic. He has done the original experiments showing that they do great on this web page classification task in '98. And also more recently, I think he has been using them in a, like at a different scale in the never-ending learning system. So it turns out that this multi-view learning is very helpful for situations where you're trying to learn many, many classes and you have many, many views potentially. And Tom will tell us about that more in one of the subsequent lectures. Okay, so this idea, this code, I guess, code training or multi-view semi-supervised learning idea can be incredibly useful for the large-scale problems that Tom has been thinking about.
Actually, can I so just to give a couple of examples, it seems like an odd assumption that you would have to implicit features.
The web page classification was a good example.
But yeah, think about, for example, email spam or any kind of email classification. You can use the title of the email and the senders, the header information, as one view, and use that, for example, to tell whether this classified email, whether it's from your family or not. Or you can use the bank of words, which is the email itself.
Sure, excellent. Yeah.
Or if you think of a robot or yourself, and you're trying to recognize a person coming down the hall, you can use sound, smell, and vision.
Okay, cool. Right, so if you want to do, say, video classification, you can use the sound or you can use the image, right? These are two natural views, right? So there are many problems, like Tom is saying, it's an excellent point, thank you, Tom. There are many problems where there are natural, right, there are natural, where it's natural to have different set of features that are, in principle, sufficient for correct classification. So that's very, very natural. Right. In terms of what's, we don't know if it's totally natural, is the additional assumption, like independence given the label or near expansion. Those are more arguable. But the fact that you, for many problems, you have two redundant set of features that are sufficient for correct classification, that's very, very natural. And actually, people have applied them. Actually, I have this on my slide. People have applied them in settings even when the two views are not so natural. They even created the views. So, for example, they have been used for object detection, where kind of they just have two different views based on two different pre-processings of the image, two different ways of doing background extraction. And somehow, even there, even if you're not, even there, co-training is very helpful. Okay, cool. So this is co-training, and it's actually, I think it's really interesting. Let me mention, I actually want to go on and to mention another different type of regularity assumption that makes unlabeled data helpful, and this is very different both from margin-based semi-supervised learning and from co-training-based semi-supervised learning. And this is a similarity-based type of assumption. Okay? And so the assumption here is the following. So assume, and I'm going to describe this mostly pictorially. Okay, so assume that we have a classification problem, right? Like maybe people identification. You want to yeah, good. And let's assume that we have a similarity, a pairwise similarity function with the property that, and let's assume that we believe we have a good similarity function. Let's assume that we believe that very similar examples must have the same label. It's a very natural assumption, right? I mean, this is pretty much the assumption that underlies the nearest neighbor algorithm, right? It's an algorithm we didn't talk about in class a lot, but it's a classic non-parametric algorithm for machine learning. And what the assumption that the algorithm uses is that we have a similarity function with the property that very similar examples must have the same label. Okay? So if we have labeled data, then we can just do nearest neighbor learning. Okay? But now, how can our unlabeled data help us if we believe this assumption that similar examples must have the same label? How can it help us at all? Well, here's the basic idea that is due to actually to Avin, Bloom, and Chuchichuala. So the basic idea is that unlabeled data can help us, right? Because we can perhaps use unlabeled samples as stepping stones Right? So in this picture here for digit recognition, so for example, this 2 is not very similar to this 2. However, it can become similar through a chain of unlabeled samples. Right? So let's assume that this is a 2, handwritten 2, this is another handwritten 2. They don't look very similar visually, but they are my labeled samples. Right? But then they can potentially become very similar through a chain of unlabeled samples. Right? So in this case, in the case where I assume that I have a similarity function and the assumption is that very similar examples have the same label, unlabeled tag can be helpful as stepping stones. Okay, so in other words, here unlabeled tag can help us glue together the objects of the same class somehow. Right? That's the basic belief here in this graph-based semi-supervised learning method. Okay, here's actually another example. So this is a digit examples here, right? Unlabeled tag can help us glue together examples of the same class. But here's actually another example. So this is here the task is person identification, and basically, right. So here, again, unlabeled tag can help. We have various types of notions of similarity between examples. So we have 2 examples are similar if they are close in time, or 2 examples are similar if they have the same color, or 2 examples are similar if a phase detector finds them similar. Okay, and this is an interesting example because right here we can use unlabeled tag to glue together objects. So for example, this image over here is not very similar to this image over here, like at first if you look at them separately, but they do become similar through unlabeled points. Okay, because for example, these 2 images are similar because they appear close in time. These 2 images are similar because of the color. These 2 images are similar because of the color, and again, maybe these 2 images are similar because of the phase detector. Okay, so right, so it turns out that there are many natural applications where you can use this insight, or you can use somehow unlabeled data to glue together objects in the same class. And this is exactly what motivated this graph-based semi-supervised learning. In these scenarios, typically we think about a transductive case where we have the unlabeled points that we ever want to predict on up front, given to us, and we have a small set of labeled examples. Okay, and the main idea here is to construct a graph like this one here, where we put an edge between very similar examples. We can even put weights if we want. Okay, and then some of the very few examples will be labeled because we have very few labeled examples, right? So we have a node in the graph for each example labeled or unlabeled, and some of them, like this one 8 here, will have labels too, right? And then the implicit belief is that similar examples have the same label, right? And then like how do you, if this is our belief, how would you label all the unlabeled points in this case? Well, what we'll try to do, we're going to try to do a partitioning algorithm, right? We're going to try to somehow run a graph partitioning algorithm where, intuitively speaking, what we are trying to do is to partition the graph into pieces where each part corresponds to one label. So in all the labeled examples of the same label go in one part. And moreover, we have very few, the edges that the edges that cut across parts have very small weight. Right? This is what graph-based semi-supervised learning does. Okay? So for example, the original algorithm of Blum and Chuala basically exactly what we do. So we are trying to basically partition the graph so that we have examples, like we are trying to come up with a partition of the graph, like for example here maybe something like this. We're trying to come up with a partition of the graph so that examples of the same label are in one component. And moreover, the weight of the edges crossing among components, those weights are minimized. Right? And that's basically what this graph-based semi-supervised learning algorithm has been doing. And then you can think about, this is what we want to do, right? We want to partition the graph. But you can ask, how can I do this algorithmically, right? And so there have been a number of algorithms on this topic. So for example, right. So for example, the original paper of Avrim, Blum, and Chuala just used forced the labeling to be hard, right? So what they wanted to do is to make sure that each example gets a hard labeling. Maybe this is a 8 or a 7, just one label, right? A hard labeling. This is what we've been mostly talking about. And they had an algorithm to do so in the case where we have only 2 labels. So it turns out that if we only have 2 labels, like it's we have lots of unlabeled data, very few labeled examples, but we only have 2 labels. And it turns out that in that case, actually, you can write a nice optimization problem for this graph partitioning problem. You can solve it in polynomial time by using the duality between max flow and min cut. So very interesting algorithmically. However, the problem quickly becomes hard if you have more than 2 labels. Okay, but luckily people have been creative, and so there's an subsequent work by Jerry Zhu, John Lafferty, and Zubin Garamani, where they have noticed, oh, if I don't force a hard label, if I allow probabilistic labels, so if I allow each example to belong a little bit to one of the classes, hopefully most prominent is one of the classes, then suddenly, and if I relax a little bit the objective, then suddenly I can solve the problem in polynomial time. And very interesting connections to random walks and so on. Right, so there have been, and this is just one example, and there have been other algorithms that have been developed based on this idea of trying to partition the graph so that examples of the same label go from the label set go on the one part of the partition, and I'm trying to minimize the weight of the bad edges that cross across partitions, right? Because the intuition there is that similar examples should have the same label, so if I have edges cutting across partitions, then it's no good, but I'm trying to minimize that weight. Okay, cool. So these are very, very different. Okay, so I'm running out of time, so I just want to mention that this, this graph-based semi-supervised learning and the code training techniques and also the margin-based techniques for semi-supervised learning, they're all based on very, very different types of assumptions that make labels are informative. And intuitively speaking, what all they do, yeah, okay, I'm going to actually stop here. I'm just going to mention that they're based on very, very different assumptions, but it turns out that you can extract a general principle that can help you understand when unlabeled is helpful. Okay, and we'll start from there next time.